like to introduce to you to our Deputy Education Director, NASA Jet Propulsion Laboratory and Manager, STEM, Elementary and Secondary Education. He also is an advisor of Mars Public Engagement Team. He has been a GPL for 25 years. Prior to joining NASA, he taught science at Beverly Hills High School. In addition to that, earning his bachelor's in geography from Cal State Northridge and master's of science education from USC, he received his prestigious NASA Expeditional Service Medal. Ladies and gentlemen, please help me introduce David Siegel.
All right, good evening, everyone. If you're eating, keep eating. Don't let me get in the way of that. So thanks for having me here this evening. As Melissa mentioned, name is David Seidel, actually. You said Siegel. That's okay. We talked about David Siegel. He was less well-behaved than me in high school, so he got called to the principal's office, and if they made a mistake, I got called, and it was like, no, we don't want you, we want the other one. So, okay, so how many of you have heard of JPL? Okay, excellent. How many of you heard of NASA? How many of you have heard of Neil deGrasse Tyson? Okay, good. All right. Okay, so the Jet Propulsion Laboratory, or JPL, is part of the National Aeronautics and Space Administration. And so the reason why you probably know of us, even if you haven't heard the letters JPL, is that we build robotic spacecraft that explore the planets. So any of you looked at the sky at sunset in the last days or weeks or so? So if you go and you look in the direction of the setting sun, there's something bright over there, that's Venus. And if you look in the opposite direction, literally turn 360 degrees and look in the other direction, that's Jupiter. So as Venus is going down, Jupiter is going up right now. So you can see Mercury, if you know where to look and when. Venus, obviously you can see Earth by looking down. Mars, Jupiter, and Saturn. If you're under ideal conditions, which if you're out in the desert and the planet is like directly opposite for the sun, meaning it's highest in the sky at midnight, it is actually possible to see Uranus naked eye. And you can't see Neptune or Pluto or most asteroids or anything like that. You can see some comets as well. The thing is, when you think about the solar system, and when you look at Venus, and you look at Jupiter, and you think about the other planets, think to yourself, and the moon, think to yourself, we've been there. We've been to all these places. Human beings haven't gone, with the exception of the moon. So there's about 24, 25 people that have gone to the moon. 12 of them actually landed on the surface. But we have sent spacecraft to all of the other planets in the solar system, of which, as Dr. Tyson might mention, there are 8. So 4 Earth-like planets, 4 Jupiter-like planets, and Pluto, which is a dwarf planet, and another dwarf planet called Ceres, and a couple of more that are even farther out. But we sent spacecraft to all these planets. So right now, there's actually a spacecraft called Messenger in orbit around Mercury. There's a European spacecraft called Venus Express in orbit around, strangely enough, Venus. There are dozens of spacecraft around Earth. We've got 2 rovers operating on the surface of Mars, Curiosity, which has been there for about 2.5 years, and Opportunity, which has been there since January of 2004. So 11 years here. This is a spacecraft that was designed to operate on the surface of Mars for 3 months, and it's been going for 11 years. And what's going to do either this month or next month is it's actually going to break another milestone. It will have completed a marathon on Mars. It took 11 years to complete the marathon, so that's not really a competitive time, but it is on Mars, after all. And the rover was only designed to drive about 0.6 of a mile, about 1 kilometer. In fact, now we're looking at 26 miles and more. So, and besides the 2 rovers on the surface, there's 5 spacecraft in orbit around Mars, 3 from the United States, 1 from Europe, and 1 from India. We've got a spacecraft that's heading out to Jupiter called Juno that will arrive this summer. At Saturn is a very successful mission called Cassini. Cassini's been in orbit around Saturn since 2004 and will continue to 2017. And there's spectacular pictures. If you've seen a really pretty picture of Saturn in recent time, it was taken by the Cassini spacecraft. We've flown spacecraft past Uranus and Neptune, and then on July 15th, a spacecraft called New Horizons is going to fly by Pluto. Meanwhile, in the asteroid belt, we have a spacecraft called Dawn, which is approaching one of the dwarf planets called Ceres. So many of you are probably sad about Pluto having gotten booted out of the ranks of major planets. So it's like, you know, it's a dog, it's a planet, you know. So I was kind of sad about it as well, but along with the other dwarf planets, Ceres was originally, when it was first discovered, identified as a planet as well. So it wasn't quite as long as for Pluto, but for a period of about maybe 40 or 50 years, if you would have looked in whatever past for textbooks about astronomy of the day, you would have seen a planet called Ceres. So the idea of things coming and going changes based on our understanding of the solar system and what's in it. So for a while, we thought Pluto was a major planet, and then we were able to make more observations of it, and it started to get smaller and smaller and smaller when we realized that, in fact, it was a small object. It's only about the size of maybe 4 of the western states of the United States, but it's still a very, very interesting place. Right now, it has an atmosphere, but as it gets farther away from the sun, it's in an orbit that's tilted compared to the other planets, and it's very elliptical, so it goes very, very far away. And as it travels farther and farther away, it gets colder and colder, and then the various constituents of the atmosphere will freeze and fall down to the surface, and we won't be able to see the surface because it'll be covered with snow, and it's going to stay that way for the next 200 years before the dwarf planet, approaches again, and the atmosphere then goes from sublimes, from ices back into vapor and has an atmosphere again. It's got at least 5 moons. We're probably going to find more. So it's an interesting place, but it just doesn't hold up in the ranks of the other major planets. So what happens is, as time goes on, you think something about the environment or about the universe or about the things in it or any area of science for that matter. And then when you learn more, you have to advance your thinking in the way we describe things to include that model. So if you find out that something is really very different than what you thought it was, but you continue to call it the same thing and you behave as if it were the same thing, and you know that it's not that, well, you're not really being intellectually honest about how you look at the science and about the knowledge of things. All right, so I understand that one of the things about you folks is that some or all of you are really interested in sciences of one sort or another. So one of the things about NASA is that we are predominantly space science, but we're also Earth science as well. So if you are understanding the planet Earth, a lot of people think that the way you measure climate is by looking outside and seeing what the weather is like. So I hear there's a difference between weather and climate. So the joke is that climate's what you expect and weather's what you get. So sometimes, it works out and sometimes it doesn't. But climate refers to areas on Earth that have typical climate characteristics over time. And they change and evolve, and there's a whole lot of different climates, from everything from polar climates to desert climates and everything in between. Well, one of the ways that you can find out what's really going on the planet is by understanding the entire planet at one time, and that's why spacecraft are important. So we just launched 2 weeks ago out of Vandenberg Air Force Base a mission with the unfortunate name of SMAP. Okay, so what it stands for is even more unfortunate. It stands for Soil Moisture Active Passive. Okay? If ever a mission was dying for a new name, this is it. So maybe it'll get renamed into something nice like Galileo or something like that, but I don't know. So what we did is we launched this spacecraft, and over the next month it has a very long boom that will be extended and a very large antenna that will be deployed. And what it's going to look at is something that is important, but we haven't been able to measure around the planet so far, and that's the actual moisture and the water in the soil itself. So we know a lot about ice, we know a lot about the oceans, we know a lot about the atmospheric water, but the water that's actually in the ground is much harder to track and to understand. And so what SMAP is going to do is it's going to orbit the Earth, and every 3 days it's going to completely map the land surfaces on Earth. So it's in a polar orbit, so as Earth turns underneath, it'll be able to map every 3 days the entire surface of Earth, and we're going to have the big picture. We're going to have literally the global picture, and we'll be able to watch it change over time. We're doing everything from carbon to looking at the biomass of Earth, measuring the gravity of Earth. We're looking at the energy that's coming from the sun. We're looking at the shape of Earth. So we're measuring everything from the core of the Earth, almost literally, all the way out to outer space and the energies that are coming to Earth. Yesterday there was a launch of a spacecraft called Discover, which is the Deep Space Climate Observatory. That's going to a point that's 1 million miles closer to the sun than we are, and it's going to sit there and it's going to stare in 2 directions. One camera is going to look back at Earth and take pictures of the disk, the sunlit disk of Earth. The other direction is going to look at the sun and measure the energies coming from the sun. And then ground-based instruments and airplane measurements and so on can be used to figure, if we know how much energy is coming from the sun and how much energy is reaching the surface of the Earth, the rest of it is in the atmosphere somewhere. And so that's understanding the energy budget of our planet. So we have spacecraft that are actually operating to examine our own environment, and there's actually more spacecraft looking at Earth than all the other planetary missions combined. So hopefully this will be a little bit of a surprise to you, but right now NASA has on the order of about 95 missions and over 120 spacecraft, so some missions have more than one spacecraft associated with them, that are either in space or in development right now. So these are real missions. These aren't missions like at JPL, we've got all these great ideas of what we could do. If we had an unlimited amount of money, look at all the things we would do. But we have actual missions that we're going to fly and missions that are in space. And so there's on the order of 100 space missions going on right now, just with NASA and the National Oceanographic and Atmospheric Administration. So I know one of the things that as you are in your academic careers here, so freshman, sophomore, junior, and senior, doesn't really matter here, right? You want to be thinking about your future in some fashion. So as you turn from your junior and senior year, you start to focus in more on what you really want to go to college to study. And I was talking with David, one of the ambassadors. One of the nice things that's different about college versus high school is right now, sure, they give you a chance to select some electives, but you haven't got that much control, do you? So your counselor is going to tell you what you need to take in order to meet the A to G requirements for the University of California, or what you're going to need to graduate on time and everything else. The nice thing about college is you can pick not only the geography of where you go, but you can also pick what you want to study. And you're going to have to take a ton of general education requirements, and it's like, why are they making me take this? But most of your coursework is going to be in an area that hopefully you've invested some time learning about, and you've decided that you're going to make the commitment to study that. So in David's case, it's computer science, or it can be the biological sciences, or physiology. It can be whatever it might be, and you're going to take a lot of coursework, but now, hopefully, you're taking work in an area that's actually of genuine interest to you. So the pressure is on, to some extent, to think about how you want to spend the rest of your life. Okay? You feeling the pressure? All right. So one of the things that high school can do for you is give you a chance to experience lots of different things. So whether it's clubs or whether it's classes or whatever it might be, you can try stuff out. And if you try it out and you seem to like it and you're good at it, hey, maybe somebody will pay you to do your hobby. So when I was growing up, I lived in this, no one's ever given me anything for this piece of trivia, but I was born in 1959, so I'm 55 now. I was born after the launch of the Sputnik spacecraft. So the space age had begun. So there were artificial Earth satellites in orbit around Earth. But it was before Yuri Gagarin had flown. So I am younger than the dawn of the space age, but I'm older than human spaceflight. Again, so what? Okay, but when I was growing up in Southern California, there was a lot of activity besides the human program. So this year actually is special because there's a whole bunch of 50th anniversaries. It's the 50th anniversary of the Gemini missions. So I think it's in March, is Gemini 3. And so Gus Grissom and John Young flew the first human Gemini mission, and then there were 3 or 4 more throughout the year. That's 50 years ago this year. And those were important because those showed how all the techniques that were necessary to fly from Earth to the moon and then rendezvous with spacecraft in deep space and come back and do spacewalks, all of those were demonstrated during the Gemini program. So when I was growing up, again, 5 years old, 6, 7, 8, 9, throughout the 1960s, I followed the human spaceflight program, but I also followed the robotic program. And in July is the 50th anniversary of Mariner 4, which is the first robotic spacecraft to fly by Mars. So up until then, all that we had were ground-based measurements from Mars through telescopes. And if you look through a large telescope, any telescope, you're limited by the atmosphere because the atmosphere is moving around. It's kind of swimming around a little bit. It's not as bad as being at the bottom of a swimming pool, but that's kind of the problem. If you ever have a chance to look through a nice telescope at the planets, any of the planets, what a lot of people do is they go up to the eyepiece, they take a look, yeah, I see it. Okay, like that was the test. Is it actually in there? Is the telescope pointing at the sky? Okay, and then they kind of march away. What you should do is, no matter who's jabbing you in the ribs, who's standing in line behind you, is take a moment to look carefully. And what you'll see is that every once in a while, the air will settle down and you're going to get a nice, sharp, crisp look at the planet, whatever it might be. And because the planet's faint, if you take a photograph, that period of time usually isn't long enough to get a sharp picture, and so the pictures come up a little fuzzy. But your eye will give you a better look of the planets than you would get through looking through a telescope, although not as good as one of our spacecraft. So that's the way that goes. All right, so the ground-based observations of Saturn included things like canals on Mars, and there was a contest, I think it was in the 1920s, where the New York Times offered a prize of a substantial amount of money for the first person on Earth to find life on another planet beyond Earth. But Mars was ruled out because that was figured to be too easy. Like that was a slam dunk. Okay, so besides the Martians, where else is there life out there in the universe? So when Mariner 4 flew by Mars in 1965, it showed that the atmosphere was extremely thin, that it was carbon dioxide, so it's like being 100,000 feet up in our atmosphere, carbon dioxide, and that every picture that showed something showed craters. And I remember thinking as a 5-year-old, well, actually I was 6 at that point here, well, that killed off the Martian dinosaurs. So the idea that there were Martians and there were canals and there was, whatever else going on Mars was killed in my mind immediately by the results from Mariner 4. Mariner 4 is also distinctive because it was the first time that the United States had pretty much beat the Soviet Union at anything. So they had a whole string of firsts, but Mariner 4, we were the ones that flew by Mars first. So there you go, a little Cold War history for you. All right, so as I was growing up, I would go to the Jet Propulsion Laboratory, and back then things were a lot looser. There wasn't even a gate there. So you go in last Sunday of the month, you could walk yourself over to the auditorium, then you could walk yourself into mission control, and then walk yourself down to the spacecraft assembly facility and building spacecraft there. Now today, I need to know 48 hours in advance, whether you're a U.S. citizen and blah, 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 blah. Now it's a whole different world, but we're doing a lot more things. So when I was growing up, my dad was into this, so I followed this, and I kind of grew up, and I was thinking, space is really cool. So to make a long story short, I ended up teaching astronomy and physical science, ran a planetarium. I was a guide at Griffith Observatory when I was in college. And thanks to a long, convoluted story that has to do with my wife's aunt, I found out about the job at JPL literally 25 years ago. So February 5th was my 25th anniversary at JPL. I got better parking now because of that. So the JPL job opened up. And basically, for lack of a better word, I'd been spending the previous, 2 or 3 decades trying to sneak into JPL anyway. Now they gave me a badge and the keys, and so now I can just walk myself into mission control anytime I want. So I managed to find a way to get paid to do my hobby in some respects. It's an area that's always been of interest and enthusiasm for me, and I found somebody to pay me for it. Now, having said that, we do not land on Mars every day. Most of the time I work for a large government bureaucracy. If I see a stack of paper and it's not bigger and not big enough, I make it bigger. And if it's standing still, I move it. Okay, but every once in a while we land on Mars, and that's created some phenomenal opportunities for me, where I was the NASA mission control commentator on NASA television for some of the Mars landings, including Mars Pathfinder, which put a lander and a rover down on the surface of Mars. So if you would have tuned in NASA TV or the local network would have been covering it, that was me you were listening to. And the thing I liked about that, not as my colossal ego let me do that, because I should have gone on television. So Dr. Tyson has millions or billions more viewers than me, but not that many people watch NASA television. But in order to be prepared for that, I had to know that no matter what happened in that control room that day, I had to know what it was, and I had to translate it into English for all the people that were watching. So it was all technical stuff. And I had to be able to translate it because everyone from folks like you to the NASA administrator to members of the science team, all the people with the white knuckles hoping the thing would work properly, were all focused and listening to me. And so whatever happened, I had to know. And so I spent literally months sitting with a team, going to reviews, going through documentation, learning everything I could about the whole entry, descent, and landing sequence, and what was going to happen on Mars and rolling off onto the surface, so that no matter what happened, was prepared. That was probably the most intensive learning experience I ever had. But I was like totally into it. It wasn't like work. It wasn't like studying for an exam. I mean, it was an exam in a sense, but it wasn't like I had to study because I had to absorb all this knowledge the night before the test. Okay, don't do that, by the way. All right, so I had months to prepare, and I was ready to go. So in 1997, for Mars Pathfinder, everything worked. Everybody was great. In 1999, for Mars Polar Lander, it didn't work. And everybody was looking at me. Okay, so if it's working and everything's great, everybody's celebrating, but if it's not working, all of a sudden the focus is on the only source of information they had. So being prepared, being ready, being good to go is extremely important. But again, the reason why it was relatively easy for me, easy is a funny word there, was because it was all in an area that was of interest and enthusiasm for me. Now, some students have identified pretty early in life what they want to do when they grow up. And it's not just, I want to be an astronaut, I want to be a policeman, I want to be a fireman. Okay, so in some respects, astronauts, policemen, and firemen never grew out of that. So I wanted to be a policeman or a fireman too, but I never really invested in that until a few years back when I became interested in urban search and rescue and things like that. So I got to do that for fun later. Okay, but what happens to most people is they have this some sort of childish notion about what it is that a particular job is or entails. And they have a childish notion because they're children. Okay? So as you get older, though, you start to get a better idea about what jobs and careers are and start to think about what really sounds good or resonates with you. Explore that yourselves. I mean, it's a very individual activity. But think about what it is that you would like to do or not. And one way to do it is get a look at a college catalog or go on a college website and see all the lists of majors. So what are the schools? What are the majors within the school? What are those things? And I guarantee it, you're going to learn and see things that you didn't even know that you could get a degree in that or there were jobs in that area. So, I mean, what's the difference in archaeology and anthropology, for example? Okay, no, I know a lot of you know that. But these are kinds of things that you can help explore yourself by going into these kinds of environments and seeing what grown-ups do and seeing what happens beyond the area of your communities and what happens elsewhere. And university degrees are a good illustration of that. So let me turn now to what you could do sort of in space. NASA there's sort of a kind of a misnomer about NASA. A lot of times NASA is described as the science agency. NASA really is more about engineering. So we engineer devices that go explore the planet. So we have scientists at JPL, and JPL is one of the places where we can do what's the entire mission life cycle, as we call it. So you can have a scientist that has an idea about a measurement that they want to make. So I'll give you an example. Jupiter's moon Europa, we know this from spacecraft missions, Jupiter's moon Europa has a salty liquid water ocean underneath an ice crust. Okay? Jupiter is about 11 times the size of Earth. Europa is a little bit smaller than our moon. And it's an orbit around Jupiter, so Jupiter just fills the sky. It just would be spectacular to see, except the radiation would kill you in about 45 minutes, but that's a different story. But underneath the ice, which protects the ocean from radiation, we know that there's organic compounds. Now, organic compounds doesn't mean life, it means carbon compounds. But comets and asteroids have these, including amino acids. They run into moons, like Europa, and planets as well, and they deposit the material on the surface. And then radiation can alter these materials as well. And if you have an ice crust, what happens, and we see evidence of this on Europa, is periodically it melts or gets slushy and turns over. So these areas that look just like icebergs, they kind of look like potato chips, but they're like icebergs that you see in the Arctic that get turned over. And what that means is that if they get completely turned over, that the material that was on the surface is now in the ocean. Now, the reason why it has an ocean is it's caught in this gravitational tug of war with Jupiter and other moons, and it's also in a very elliptical orbit. And what that's doing is it's causing the moon to flex. So have you ever been a paperclip? Bend a paperclip really fast before it breaks, it gets hot? Well, essentially, the moon is doing the same thing, and the rock crust and metal is flexing back and forth, and that creates enough heat to melt an ocean. So let me cut to the chase. Hopefully, in your lifetimes, you'll have a chance to come to JPL and work on a mission that would put a lander on Europa, leave the batteries and the transmitters at the surface, melt its way down, paying out a cable as it went. As it melted way down, it could stop periodically and have a little auger that would be able to drill into the ice and examine it, but get down to the bottom of the ice column and release a hydrobot, a mini submarine, that they could then go and explore the deep ocean vents on Europa. It's not at all out of the question that there's actually, right now, sea monsters swimming around in the oceans of Europa. And in many respects, Europa is actually a better prospect for life than Mars. There's still a chance that we might find microbial life on Mars or evidence that existed in the past. But today, there could be sea monsters swimming around in the oceans of Europa. Okay? Well, needless to say, we would love to go there. Right? So we have a mission that's going to take several years to develop and fly called Europa Clipper, which is going to help us characterize the thickness of the ice, among other things. But we actually have demonstrated all the components necessary to go to Europa and do the mission I just described. So if you think that's cool and you'd like to be on the team that discovered the sea monsters on Europa, see, what I envision is that there's like the hydrobot's got a camera and a light because it's going to be dark down there. And so it's swimming along here, and then the very last picture is of teeth, and then the signal goes dead. Okay? That'd be awesome. Okay, that is a real mission that you guys could come. I don't know I'm not sure about the last part there, but this is a real mission or set of missions that you could come to JPL and work on. Now, if you want to work on that mission, you're probably going to need to be an engineer of some sort. So you can be a scientist as well, but engineering is mechanical engineering, computer science, electrical engineering. There's a whole range of engineering disciplines that are involved with working on a mission like that. So let me tell you a dirty little secret about how careers work at JPL and other places as well. You're going to get hired for your first job based on your qualifications, your academic preparation, and what you've done that makes you look like a good candidate. So at JPL, we have a program to hire early career hires, ECHs. These are people within a year or two of their degrees. So you get out of college, come to JPL under this program. And no matter what our hiring is, it's like, well, we don't need anybody this year. We're still going to hire ECHs. And the reason is there's plenty of old guys that are getting older. So we want to have a younger workforce coming in. And so we hire ECHs that are coming in because they're prepared for an environment like JPL, and they're pretty much prepared to start at the bottom. Okay? Because a lot of what happens in space exploration design has to do with lessons learned. And you've got to work on projects for a while before you've kind of learned enough lessons to kind of move up in the food chain. Now, having said that, we have a program that actually gets early career hires a chance to work on flight hardware early in their career. And so there's some hardware on the International Space Station that was essentially built by students and designed by students and engineered by students only a matter of maybe 3 or 4 years out of college. So your chance to actually put stuff in space is pretty good. And you can go to a program that works with CubeSats. So CubeSats are 10 centimeters, about 4 inches on a side, and they're cubes. And they go along for the ride on rocket launches for larger spacecraft. So there's a lot of college programs that are building space hardware that are flying piggyback on other missions. So again, as an undergraduate, you could actually get hardware into space if that was interest to you. I mentioned you get hired for your first job. So say at JPL we need a thermal engineer, someone who understands how heat moves through systems and structures and so on. And so we'll hire a student that has got some coursework and preparation in that area. So we're not going to hire like a computer scientist to do thermal engineering. That would be mean. So we're going to hire someone who's got some experience doing thermal work. Then that job's going to end. So what do they do next? Well, there's probably other thermal work going on. But if they do a good job and they've got a reputation for themselves and their group supervisor kind of shops them around a little bit, someone might say, yeah, I heard about that guy or that girl. I mean, she was really good. Did good work, delivered on time, elegant design, whatever it is. I want her to work on my project. It may not be a thermal engineering project. So your career, or your academic career was involved in engineering courses dealing with thermal, and you hired at JPL and you got a thermal job. Now somebody else wants you to do mechanical engineering. Well, they don't care that you did good on thermal. They care that you did good and that you learned and that you had a lot of other things that you absorbed during working on that mission. And you end up working on something else. The next guy might want you for communications. And so over the course of your career, if you think you're going to come to JPL and spend your entire happy career doing thermal, you might. But if you want to be a project manager, which is arguably the most important job at JPL, so everybody above and below in the management chain is working for their success because we do missions, those people have done everything. So John Callis, who's the manager of the Mars Exploration Rover Project, this is a rover that's been on Mars for 11 years, or another way of putting it, it's as if you live to be 3,000 years old. This rover right here, the project manager, John Callis, he's actually a scientist who learned a lot of engineering. So he started out as an Earth system scientist. The work dried up there. He started working on Mars, and not before, it took a while to get there. He had a whole lot of different jobs in engineering and so on. His academic preparation, the sciences. So make sure that when you find something interesting or exciting that you enjoy, that you then kind of keep your mind open to what else you can learn and what else you can be open for. Now, something about jobs in this particular sector. There's about 5,000 people that work at JPL. Okay, we're in Pasadena above the Rose Bowl. Actually, it's really locking you out of Flint Ridge. So we explore the solar system from Pasadena. There are 9 other NASA centers located around the country, plus NASA headquarters. And at those locations, there are government employees called civil servants. At all the other locations, there's only about 17,500 more. So there's about, in round numbers, about 25,000 NASA employees. But there's about 400,000 contractors that work on behalf of NASA for companies like Boeing, Lockheed Martin, Northrop Grumman, Raytheon, on and on and on. So there's companies large and small, and NASA doesn't build its own rockets. So the rockets on which we launch our spacecraft are built by corporations that bid for the work and compete for it. The space shuttle was not built by NASA. It was built by a company called Rockwell International, which then became part of Boeing. The International Space Station is operated by Boeing, essentially. And the hardware is built by different countries, including Russia, and it's all integrated together. So NASA isn't the only way to work for exploration of space that way. And now there's an exploding new sector in the private sector that has some to do with NASA, but not necessarily everything to do with NASA. So now companies like SpaceX, heard of them? Okay, SpaceX builds rockets and they build spacecraft and they get contracts from the government to fly things. So the Discover mission that I mentioned, the one that's going to stare at the sun and stare at Earth, was launched on a Falcon 9 booster. So NASA purchased that booster from SpaceX. Something else that happened yesterday is a SpaceX capsule called Dragon, which has been docked to the International Space Station for about 3 or 4 months, I think, separated from the space station and landed in the Pacific Ocean about 300 miles that way. Actually, 300 miles from the coast, so I had to drive for like 100 miles this way to get here, so 400 miles that way. So it brought cargo back from the International Space Station and science experiments on a contract with the government to bring cargo up and bring cargo back down. And they're qualifying a spacecraft that will be able to fly human beings. So instead of, right now, United States astronauts flying on Russian spacecraft, what's going to happen is we're going to contract with SpaceX or with Boeing, who's also building a spacecraft called CST-100, and we're going to buy seats. So we're not going to own the taxi service. We're going to buy seats on the taxi. And when it's time for us to go to space, I mean, you have to schedule these things. It's not like you go out and you wave and say it's time to go to space. You don't have to schedule these things in advance. But we're going to purchase seats from SpaceX and or Boeing and then use them to get to and from the International Space Station. So now there's all these other kinds of companies out there that are interested in people that are interested in exploring space. And it's not just engineers, not just science. It's also marketing, the whole business model. If you're running a company, you need an effective business model. Otherwise, your company isn't going to work just because you have good thoughts. You need to do all the publicity and marketing for that, and so on. So there's a lot of different types of careers that are all focused and centered around exploring space. And there's also the area of space tourism. So Virgin Galactic had an accident. They're going to have to certify their spacecraft to fly humans, but for a mere $250,000, you could go up into space and fly a ballistic trajectory, be in outer space for 6 minutes, and then come back down to Earth. Okay, who's got $250,000 to do that? I don't. Maybe one of you could let me borrow that. We'll see. But now the idea of people going into space for non-scientific or technical reasons is opening up as well. And there's a market for it, although there's not a lot of people. But when I look back in time, when my grandfather was a kid, the only way to get across the Atlantic was on a steamship. Now anybody can go to the airport, buy a ticket, and fly across the country or around the world. Whether space ever is quite like that, I don't know. But there's a guy in Vegas named Robert Bigelow who's interested in building space hotels. Okay, and he's got 2 prototypes that are flying in space right now. These are inflatable structures where human beings would be able to go to, whether it's Virgin Galactic or some other company, they'd be able to buy a ticket to go to a space hotel and spend a day or a week or a month up there and then fly back down, and the government had nothing to do with it. Okay? Interesting businesses. The reason why Bigelow's interested in this is he actually made his money in, I think it was budget inns. So he did hotels and that kind of thing. So that's kind of where he's thinking. So a lot of opportunity, a lot of things to think about in terms of the sector, the space sector. It's not just working for NASA. It's not that you have to be an engineer per se. Lots of opportunities in the sciences, in business, and so on. So keep an open mind. One of the most valuable things you can do as a student is learn how to learn. I'll give you an example. How many of you are taking AP courses? Okay, great. In AP courses, you don't just show up in class and take the class and then the test at the end. You're responsible for a ton of homework and learning outside of class. When we look for interns at JPL, AP courses tell us that you have learned how to learn. Okay, you've taken responsibility for your own learning. That's going to be huge when you get into college. That's going to be huge when you get into a career. So good luck to you all, and I'm looking forward to seeing many, if not all of you, apply for internships when you get into college and coming and working on that Europa mission, because if they're sea monsters, I definitely want to find them. So, what do you think?
Thank you, David. That was really interesting.
Thank you, Mr. Seidel, for coming over to meet with us, and Dr. Tyson will be here in just a few minutes.
Welcome, student sponsors, to the second event of the Youth Desert Talk Hall 2015. A very special speaker will be joining us shortly. He, like myself, has an unquenchable passion for the physical sciences. when I was a kid. I remember watching various educational and scientific channels that lectured audiences on subjects like physics and biology. One Saturday morning, when I was still in my pajamas, I remember watching a program about space exploration. I remember the astronauts in their bulky spacesuits putting on some upgrades on the Hubble Space Telescope. I could see the shiny gold foil, the breathtaking view of the Earth, and the space shuttle Columbia. Ever since then, I've harbored dreams of working for NASA. Now, as a son of immigrant parents from Mexico, never in my wildest dreams could I have imagined having the honor and the privilege to be able to introduce one of America's most distinguished astrophysicists. He is an author of several books, including his most recent, Space Chronicles, Facing the Ultimate Frontier. He has hosted several media programs like Cosmos, A Space-Time Odyssey. He has his own talk show, Star Talk. He is currently the director of the Hayden Planetarium in New York. Ladies and gentlemen, he is Dr. Neil deGrasse Tyson.
Thank you. Thank you. Hey, everybody. So everyone here in high school? Yeah. How many seniors are here? And juniors? And sophomore? Freshmen? 5 freshmen. Cool. Cool. I believe it or not, I remember high school vividly, and I would say it was the most formative years of my life were in high school. I went to a high school that I went to a nerdy high school. It was called the Bronx High School of Science. And what was fun about going to a nerdy high school is that between classes and during study hall and lunch, our conversations would be about the universe and not about other things. And that had me realize that you'll spend more time not in school, more time between classes, more time eating lunch, more time commuting to and from school than you will ever spend in school. And so the more you can engage the time that you're not in school, learning and thinking and dreaming, much farther you will get in life. There are so many people out there who view school as some kind of a chore. Ask any adult if they had the choice where their only job was to learn, or whatever it is they're doing now, they'll take going back to school in a heartbeat. And so whatever, I don't know what you think about high school, but your only job is to learn, and you should celebrate that fact, is what I'm saying. So I'm told you guys were chock full of questions about life, the universe, and everything. Is that right? Oh, by the way, did you bring your teachers with you too? Raise your hand if you're a teacher. Cool. Maybe we'll take questions from teachers later. From students now. Did they come up to the microphones?
So students, if you have questions, please join me up here at this microphone.
Okay.
Don't be shy. Make a line.
Are we ready? Okay, and tell me your name and what year and what you want to be when you grow up. How about that? Okay.
Hello, Dr. Tyson. My name is Josh Freeman. I'm from Palm Springs High School, and I'm a senior. As for what I want to be when I grow up, I'm not entirely sure.
That's a perfectly fine answer. Right.
But for my question, with the current innovations in propulsion technology, like the nuclear pulse propulsion system of the Orion spacecraft, will manned expeditions to the superior planets be feasible within my lifetime? And if so, what steps need to be taken?
Yeah, so that's a great question. And it turns out, if you want to jet around the solar system, so you're talking about the major planets, you hurt Earth's feelings by saying Maybe. Just want you to know. You mean the larger planets, yeah. Right. So Jupiter, Saturn, Uranus, and Neptune. So you want to go there. It'll take a while, right? The problem is we only live a certain amount of time, and being human beings, and our current propulsion, depending on where you choose to go, could eat up most of your life getting there. And we have a rule in science that whatever experiment you're going to perform, it has to be finished before you die, right? This is the rule that we have for ourselves. So this propulsion that's there, it's enough to get us to the outer planets with humans, but that has never been engineering has never been the challenge of space exploration. The challenge has been funding. It's only ever been funding. So you tell an engineer, I want a ship to get there in 10 years and with food, they'll build it. That's what engineers do. They live for that. But you got to come around, and there's Congress, and then there's the public, and are they voting for that, or do they not care? And so it's a complicated, messy thing. The science is easy. The politics is hard. So, no, you're not going. The way things are going, no, that's not going to happen in your lifetime.
Thank you.
Wait, but. I don't want to leave you depressed. So we live, at least we tell ourselves, we live in a democracy. And in a democracy, you don't really have the right to complain about anything. You have the right to change it. Think about it. If we were a dictatorship, you complain. Yeah, complain. Go ahead. You can't change it, but complaining gets it out, right? In a democracy, to say, why isn't this another way? Get out there and change it. Run for office. All right? Start a campaign. That's how democracies work. By some subset of people in the population who see a future that's different from wherever everyone is headed. And it sounds like you see that future. So be the change that you seek to happen.
Thank you.
All right. Next.
Hi, I'm Chloe Wood. I'm a junior at Palm Desert High School. I don't know what I want to be yet.
Good answer.
If you were my age now, what project would you want to work on?
If I were your age now, I think I would still want to be an astrophysicist because it's just coursing through me, and it's been that since I was 9. So when I was your age, it was still coursing through me. So the way I'll answer that is, given that we live in a multiverse, perhaps, what might I be in another universe if I were your age? And so here are topics that would intrigue me. Nanotechnology intrigues me. You can only build things as small as your smallest tools will allow you. So if you want to build new molecules, you need tools that can manipulate molecules. We build structures, and we have bulldozers and bricklayers and things because we now have tools that can maneuver things that size. And we can build structures made of that. So I think the future, a huge future of our science and technological civilization will be our capacity to manipulate and control very small entities such as atoms and molecules. So that's probably what I would lean towards, and those are the projects I would work on.
Thanks.
Okay, good. Yeah. Is that an image of me on your shirt?
It is. Yeah.
Wow, cool. Wow, and what does it say?
It says Neil deGrasse Tyson for president.
Wow, okay. Okay. So before you ask whatever your question might be, I'd like to respond to that shirt. Mm-hmm. I'm officially... No. No. I just realized there's a whole sector behind you guys that I can't... They're like... You're like the front line of the Green Bay Packers, you know? Nobody can see past you guys. How How about, because I got to see people. I'm like looking at people back there. Oh, you guys aren't the students. Oh, forget you. No, well, we'll deal with you later. Oh, sorry about that. Okay. So, the New York Times asked me what I would do if I were president. They asked me that at one particular time where there was this impasse in Congress. And they thought maybe some other professions not traditionally associated with politics, maybe they have a bright idea, because apparently no one else did in Congress. But my reply to them, I think, was unorthodox. I said, if I were president, I wouldn't be president. Because the very question, what would you do if you were president, presumes that the challenges of the nation derive from who's president and who isn't president. When in fact, we elect presidents. So if you're going to take a president and swap it with somebody else, there's still the matter of the electorate that you need to deal with. And the electorate has preferences and priorities. And so you can't just swap leaders out in a democracy. That's not how this works. So my reply was, as an educator, so here we are as an electorate, electing people into Congress, and Congress is dysfunctional. And we blame Congress. But we elected them. So who is ultimately to blame? We are. So as an educator, I'd like to educate the electorate in whatever way can help serve their decision-making so that they can elect someone to office that will not end up in daily impasses, bringing the government to its knees. So I have no interest in such positions, and I'm quite happy being an educator along the way. Now, I guess you had a question. Yes.
Wait, so I should buy a new shirt?
I'm going to tell you what to wear. No. Mm-hmm. So you had a question. Sorry that it took so long to get to it.
Could you measure the size of a space-time singularity, like say with Planck length, or is it smaller?
Well, everything we know about the center of a black hole, for example, which would be a singularity, all the matter collapses with no known force to resist it. By the way, the singularity is the limit of Einstein's equations. When you're there, you're practically dividing by zero. And you may have learned from your math class that's a no-no. So we already know that's the limits of Einstein relativity. And so we're sitting there waiting for some idea to help take us to the singularity itself. String theorists are assisting this effort. But we know of nothing to stop it. So here's the thing. General relativity doesn't know anything about Planck lengths. This is the smallest unit of length that exists in the known universe. Quantum physics knows about Planck lengths. And these two theories do not communicate with one another. That's why we have string theorists who are trying to say, well, is this going to win out of that, or is there a third understanding of the universe that will enclose them both? So it is a frontier of the cosmos.
Can string theory exist with quantum mechanics?
Yeah. But something has to give. These two theories of the universe are incompatible, yet they work in their own regimes. In the early universe, when the large was small, you had a shotgun marriage between general relativity and quantum physics. So whatever theory they're working on, that's the testing ground for it. And so these huge particle accelerators are simulating the energies of the Big Bang, and that's where we test these theories of everything.
So a space-time singularity is like infinite dense and...
We don't know. We don't know. It's a frontier. You can make stuff up, but that wouldn't be science. It would just be making stuff up. And then you can make stuff up and then make a movie out of the stuff you make up, and then it's science fiction. Right? We should keep the line moving, though.
Yeah. Thank you so much.
Okay, good. Sure. Next. Hi.
Good evening, Dr. Tyson.
Hi.
My name is Mercedes Garcia, and I am a senior at Palm Springs High School.
Thank you. And you want to be when you grow up?
I would like to be a writer.
A writer, okay.
Yes.
You can just be one, You can start now, and then you say you're a writer.
Okay,
Right,
I'm
good.
a writer.
Okay. No one has to certify you. I'm now a writer, but yesterday I wasn't, right? Okay.
I have been and always will be a writer.
There you go. Writers, they write from their heart, and that's how you know you're a writer. No one has to tell you that. No one has to certify you for it. Yeah.
Thank you.
I interrupt. Go on.
In your opinion, what single piece of knowledge has impacted the progress of astrophysics the most, and why?
Single piece of knowledge, I would say equals MC squared.
Oh.
Yeah. There's that. I wrote an entire essay on E equals MC squared, and in fact, I won an award for that essay. They gave me a chair, actually. I wanted money, but they gave me a chair. Oh. But on the back of the chair, it cites the name of the essay, and then I'm the award winner. E equals MC squared drives this universe on levels that we're less familiar in our everyday human life. But it was there at the Big Bang. It's there at the formation of galaxies. It's there at the formation of stars. It's there during the entire life of a star. It'll be there when the universe ends. It is driving everything that's going on. It's a profound equation. It took a profound scientist to come up with it, obviously Albert Einstein. So it's a cornerstone of modern physics.
Thank you very much.
Okay, good. Hello?
Oh, hi. My name is Juan Felix. I go to Rancho Mirage High School, and I don't know what I want to be when I grow up yet.
Good. It's all good.
Yeah.
Uh-huh.
If you could meet any scientist that has ever lived, who would it be and why?
Yeah, it'd be Isaac Newton. There's no question about it. Isaac Newton. And I think he was the smartest person there ever was, ever. All right? And people say, well, how about Leonardo? How about Einstein? And I like me some Einstein, don't get me wrong. But if you just look at what Isaac Newton did, you know, he discovered the universal law of gravitation. He discovered the laws of optics. He discovered the laws of motion. When challenged about why his law of gravitation made orbits in the shapes of ellipses, he would go home, and because he didn't have an answer just yet, so I'll get back to you. He goes home, comes back, and here's why you have these ellipses. And his friend said, well, how did you get that answer? Well, I had to invent integral and differential calculus to find this problem. Then he turned 26.
That's awesome.
I would bring Isaac Newton into the present and have him solve all of our problems. That's what I would do. Now, here's the challenge. I think about this all the time. So I'm having a dinner party, and Isaac Newton is my special guest. So I bring him through some space-time continuum wormhole, and now he shows up at my table. Okay? And then I realized his head would just explode. Because I would go to the wall and flick a switch, and then lights would show up above his head. That would just freak him out. That doesn't happen in 1704, right? And there'd be these things moving in the street, horse-drawn carriages without horses. And he would say, well, what is that? I say, well, it's a horse-drawn carriage without a horse. We call them cars. Well, what makes it go? I would say gasoline. Well, what's gasoline? Well, we get it from oil. Well, what's oil? Where'd that come from? And what's an engine? And the whole thing, I'm just be explaining what the hell he's looking at the whole time, right? This is what that would, and so I realized how challenging this would be. And the advantage, of course, he's British, so that we would not have a language problem. Because if you bring, like, Aristotle into the present, he's speaking Greek, and I don't know Greek, and that's the end of the dinner, right? So I think about this all the time. All the time. And then if I was going to show him something that'll freak him out, I just pull out a smartphone and show him a calculator. And he would spend weeks on calculations that I can just do in a few seconds. And I can, like, play music on my smartphone. He said, how'd you get an orchestra inside there? You know, these are the questions I think he would ask. That has me wondering, if any one of us or I were, like, transported 300 years into my future, our future, how freaked out would I be about what's going on around the dinner table? And I look forward to that. I want to live a long life so that I can see a completely new world. If the world looks the same today as when I'm dying, we all failed, as far as I'm concerned. But thanks for that question.
Thank you.
Yeah, good. Hi.
Hi, I'm Stephanie Robinson. I'm a senior at Palm Desert High School, and I'm interested in chemistry.
Chemistry, cool. Mm-hmm. And chemistry is interested in you. Yet we are all these sacks of chemistry functioning as in a form of what we call life. Yeah. So, what do you have?
What do you think of the universe's heat death, and what would this universe be like?
Yeah, we are in a universe that's it's called a heat death, but it's a little misleading. It's really a cold death. It is a universe, but the reason why we call it a heat death is because there's no such thing as cold. Cold, what we say is cold, is the absence of heat. So we are in an expanding universe. The temperature is dropping, and the temperature will continue to drop until it reaches zero. When the universe reaches zero temperature, all things end. And there's a famous poem, I think it was by John Updike. The universe will end not with a bang, but with a whimper, not in fire, but in ice. So, yeah, it's trillions of years from now. So it's not something you should distract yourself. You should instead study your chemistry in school. But it's a fascinating future that we face in this universe. It's a one-way trip, philosophically unsettling to many people, actually, because they want it to always be, to be the same or to cycle. And as a scientist, you can't invest emotion or philosophical priorities into what your experiments are. You might end up biasing them, and you just need to let the universe speak for itself. And the universe has done so. We're on a one-way trip to an expanded oblivion. Have a nice day. Next question. Yeah.
Thank you.
All right. Hi, my name
What? There were like 10 people behind you in line. What did you just do?
I asked them nicely if they could leave.
Oh, okay. All right. So what do you got?
My name is Gustavo Garza. I am a junior at Indio High School, and I want to be a computer engineer when I grow up.
Mm-hmm.
And my question for you is, do you believe time travel is currently possible, or will it be in the near future?
Time travel is entirely allowed in the laws of physics, time travel into the future. In fact, GPS satellites, okay, are slowly moving into our future because of their position in space. They're 500 or so miles above Earth's surface. They're in a different gravity field than we are. And the higher is the gravity field you're in, the slower time ticks for you. So that those GPS satellites have actually are older, according to their own clocks, than our clocks would measure them to be. Now, we knew this in advance. This is Einstein's relativity manifest even in our own technology. And so the time that the GPS satellites gives to your cell phone, to your mobile phone, because that's where you get them off of cell phone towers, but globally ultimately that's where the times come. Yeah. That time has been pre-subtracted to compensate for the fact that it's beaming a time into a different gravitational field. Pre-subtracted. So, we already know how to move forward in time. We can do that. And so the question is, can you do it enough for it to make any kind of interesting difference in anybody's life? You'd have to move like half or three-quarters the speed of light for a really long time, and then come back, and then you'd be like younger. Then if you did that, then you'd outlive everybody else around. I mean, it's an interesting phenomenon. You say, well, how do we know? Do we have evidence of that? We have particles that decay into other particles at a very specified amount of time. When you put them in a particle accelerator at high speeds and run the equations of Einstein, we say time ticks more slowly for them. Their internal clock has slowed down. By how much? By a factor of 2. How do we know? Put them in the accelerator, it takes twice as long for them to decay. This is real. We've done the experiments. So, yes, we can go forward in time. The problem and the challenge would be, can we ever go backwards in time? Should we ever go backwards in time? Suppose I send you backwards in time and you accidentally prevent your parents from meeting. Then you are never born and you could not go back in time to prevent your parents from meeting. So, in Terminator, the film, There was just that scenario, except since it's a movie made in America, it was just violent, right? They wanted to kill the mother of the person who would lead the revolution against the machines. This was the premise of Terminator. So the machines sent someone back in time to kill the mother. Okay? All you have to do is prevent the mother from meeting the father. That's all you have to do. Or have them have sex at a slightly different time than they did to give birth to the leader of the revolution, and they will give birth to a different child. That's all it would have taken. But no, James Cameron had to kill everybody just to make that happen. I know it would have been a less interesting movie if you just sort of bumped someone away to delay. But anyhow, going back in time could be seriously dangerous for the world that you've come to know. And we have people thinking about what would happen if that were ever enabled. One bit of evidence that maybe we've never invented backwards time travel is that maybe we would have seen that by now. Then it was suggested that maybe Isaac Newton was sent back in time to be Isaac Newton in his day. Maybe Albert Einstein was from the future sent back in time. These are people who are way beyond anybody's understanding of the world at the time. So that would be an awesome science fiction story if you wanted to play that one out. But anyhow, I saw a guy. There's a great sign on the great picture on the internet. There's some nerds protesting, okay, and it said, you know how you have protesters say, "We want change. When do we want it? Now, right?" This is how this protests go. Okay. We want a time machine. When do we want it? Well, it doesn't really matter. Thank you all for hanging out.